Okay, Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera kelas. Okay, in today's lesson, we are going to look at another two questions for your tutorial 6.2, question number 10, and also question 11. Okay, so let's start with the first question, question 10. All right, so now let's read the question. So what do we have here? We have nitrosyl bromide, okay, and OBr decomposes to form nitrogen monoxide and bromine, okay, and the three of this, okay, are at equilibrium, right? And then let's say if 2 moles of nitrosyl bromide in a 1 liter flask decomposes to give 0.09 moles of bromine at equilibrium and the temperature is 77 degrees Celsius. Determine the equilibrium constant Kc and Kp, and lastly determine the degree of dissociation of nitrosyl bromide. Okay, class. If you look at this question, actually this question is quite differ from the previous questions that you have encountered so far. Okay, in this question, actually, this time we were given the moles of bromine, but okay, class, but the given moles here is moles at equilibrium. See, this 0.09 moles of bromine here actually is the mole of bromine at equilibrium. Remember, this is not initial mole. Okay, this is moles of bromine at equilibrium. Okay, so however, still we're going to start to solve this problem A, 10A, by constructing the ice table first. And so let's look at, okay, how to construct the ice table. Okay, so as usual, uh, so we are going to start with the initial concentration, the changes in concentration, and also the equilibrium concentration. Okay, so for nitrosyl bromide, okay, since the moles and the volume of the flask, okay, were already given in the question, right? So 2 moles divided by 1 liter, so we are going to get 2 molar plus 2 molar. So this 2 molar is the initial mole of nitrosyl bromide, and we are going to bring this 2 molar and we are going to put this 2 molar inside here, okay, as the initial concentration of nitrosyl bromide. Okay, and initially both of these two gases, nitrogen monoxide and bromine gas, both are 0. Okay, why? Because this nitrosyl bromide has not decomposed yet to produce these two gases. Okay, so that's why both of these initially are 0. Okay, and then once this NOBr or nitrosyl bromide starts to decompose, so what happened to these two gases, nitrogen monoxide and bromine? So these two gases starting to form, or we can say that these two gases, okay, started to be produced, okay, in this reaction. Okay, and we know since nitrogen bromide is a reactant here, happen to reactant, okay, the concentration, okay, decreasing, will be decreasing. So in this case, the concentration of nitrosyl bromide decreased. Okay, so the changes, the changes of the concentration of nitrosyl bromide, okay, will be decreased minus 2x. Okay, but for nitrogen monoxide and bromine, so these two gases shall increase their concentrations. Okay, but for nitrogen monoxide, so since there are 2 moles of nitrogen monoxide here, so the changes would be increase, okay, 2x. Okay, and then bromine just plus x. Okay, and these changes, okay, these 3 changes are going to happen until, okay, all of these 3 gases reach equilibrium. Okay, reach equilibrium. And at equilibrium, okay, the equilibrium concentration of nitrosyl bromide would be 2 minus 2x. Okay, and nitrogen monoxide 2x, and bromine x. But remember, in the question, we were already given the moles of bromine at equilibrium. And therefore, actually, we can use the given mole, okay, to determine the value of x. So since the volume is 1 liter, volume of the flask, so therefore 0.09 divided by 1 liter, so we are going to get 0.09. So meaning that this is the x value. Okay, x value is 0.09 class. Okay, and then since this is the value of x, so we can substitute this x value into these two places here. Okay, so first we can substitute into this x here. So 2 times 0.09, so we are going to get 0.18 class. So this is the concentration of nitrogen monoxide at equilibrium. Okay, and then we can also determine the concentration, okay, of nitrosyl bromide at equilibrium. So 2 minus 2x, so since x is 0.09, so therefore if we calculate this, okay, we are going to get 1.82 class. See, so these are the three equilibrium concentrations for nitrosyl bromide: 1.82 molar, nitrogen monoxide 0.18 molar, and bromine 0.09 molar class. Okay, so once we have already calculated this three concentrations, so the next step that we are going to do, okay, we are going to substitute, okay, the three of this into the Kc expression, because in question 10a, okay, the question asks you to find the value of Kc. Okay, and then this is the Kc expression, okay, for this reaction. So Kc equals to the concentration of nitrogen monoxide at equilibrium squared times the concentration of bromine at equilibrium divided by the concentration of nitrosyl bromide at equilibrium squared. And therefore, if we substitute these three values into this equation, okay, and then we calculate this, and we are going to get 8.8 times 10 to the power of negative 4. So this is the Kc value for this reaction. Okay, and then the next step is we need to determine Kp class. Okay, we need to determine Kp. Do you still remember what is the relationship between Kc and Kp? You still remember, class? Okay, so Kp equals to Kc times RT to the power of delta N. So this is the relation between Kp and Kc. Okay, so right now, before we can use this equation here, so first of all, we need to find out, okay, what is the value of delta N first here, class. We need to determine this first. Okay, so in order to determine the value of delta N, so now let's look back at the equation. Let's look back at the equation given. Okay, right. So now we're going to find delta N again. Okay, right. So as usual, delta N. So what is delta N? Mole of gaseous products minus mole of gaseous reactants. Okay, so from the equation, okay, delta N equals to 3 minus 2. Okay, why 3 minus 2? Okay, if we look at the product side here, so how many mole of gases are there in this equation? So 2 plus 1. See, 2 plus 1. And therefore, here got 3 moles of gases. While on the other hand, on the left side here, or on the reactant side, okay, there are 2 moles of gas, okay, 2 mole of nitrosyl bromide gases. Okay, and that's why 3 minus 2. Okay, and 3 minus 2 is 1. So therefore, the value of delta N is 1 class. All right, then, okay, we write the equation, okay, Kp equals to Kc times RT to the power of delta N. Okay, since Kc already determined just now, okay, 8.8 times 10 to the power negative 4. So we are going to substitute this into here, and then R, what is R? Gas constant, 0.08206 liter atm per mole per Kelvin, and then the temperature. So the temperature given, but keep in mind, class, if the temperature given is in Celsius, we need to convert it into Kelvin first. And then we substitute into this equation. Okay, then delta N is 1, right? So by substituting all of these values, so this is what we are going to get, right? And then we calculate this, we solve for this, and we are going to get the value of Kp is 0.025. Okay, class. So this is the value of Kp and value of Kc for this reaction at equilibrium. All right, next. Okay, so the next part of this question, the question asks you to calculate the degree of dissociation, of this nitrosyl bromide, right? Okay, remember what is the formula to calculate the degree of dissociation? Alpha, remember, alpha, okay, alpha, degree of dissociation equals to changes in concentration of nitrosyl bromide. Okay, so that's why I'm using this symbol here. Okay, this triangle stands for changes or delta, changes in concentration of nitrosyl bromide. Okay, so divide by the initial concentration of nitrosyl bromide. Okay, you still remember? Okay, so what is the changes of concentration of nitrosyl bromide? Remember from the ice table, class, 2x minus 2x. So that is the changes. That is the changes of the concentration of nitrosyl bromide. So we're going to, okay, firstly, we write it as 2x. Okay, this is the changes of the concentration of nitrosyl bromide, and then divide by the initial concentration of nitrosyl bromide, which is 2 molar. Okay, so since x, we have already determined the x value just now from the ice table, remember, 0.09, right? So 0.09 times 2 divided by 2 molar. Okay, so molar and molar cancel. Okay, and what are we going to get for the answer here? The answer is 0.09 class. So this is the degree of dissociation of nitrosyl bromide. Okay, class, let's say the question further asks you to find the percentage of dissociation. So how to convert from this 0.09 into percentage of dissociation? Okay, yes, simply we just multiply by 100%. And let's say if you want to convert from degree of dissociation into percentage of dissociation of nitrosyl bromide, so what we are going to get? So 0.09 times 100%. Okay, so we are going to get 9% plus. Right, so what is the meaning of this 9%? Okay, so this 9% here means at equilibrium, okay, at equilibrium, only 9% of nitrosyl bromide decompose or dissociates to form nitrogen monoxide and bromine gases. So that is the meaning of this 9%, or also known as percentage of dissociation of nitrosyl bromide. Okay, so that's it. That is for question 10. Okay, so now let's move on to the Next question, question 11. Okay, question 11. So let's see what do we have here. Hmm. Okay, so this time we have iodine vapor class. Iodine vapor. Okay, when this iodine vapor heated at high temperature, so this iodine vapor dissociates as follows. Okay, so iodine vapor dissociates to produce iodine gas. Okay, atomic iodine gas. Okay, atomic iodine gas. Right. Okay, and then in one experiment, a chemist found that this 0.054 moles of this iodine vapor, okay, was placed in a flask of volume 0.48 liters with a temperature of 587 Kelvin. The degree of dissociation was 0.252. Remember, degree of dissociation actually to this 0.0252 actually is the value of alpha. Okay, alpha, the degree of dissociation. Okay, and then the question asks you to find out what is the value of Kc and what is the value of Kp, okay, for this reaction at this temperature, meaning that at the same temperature 587 Kelvin here. Okay, so this time we are going to do backtracking. Okay, so why did I say backtracking? Because in the previous question number 10, okay, we need to determine Kc and Kp, and later we determine the value of degree of dissociation or alpha. So in this case, in this question, question 11, this time alpha is given. Okay, alpha is given in the question, and from this value of alpha, we are going to determine Kc and Kp. Remember the difference between question number 10 just now and this question 11. Okay, right. So as usual, we are going to start with ice table. Okay, and then rewrite the equation. Okay, the equilibrium between iodine vapor and gaseous iodine atoms. Right, and then we're going to start with the initial concentration. Okay, so initial concentration, moles given, the initial moles of iodine vapor, divide by the volume 0.48 liters, and we are going to get 0.1125 molar. Right, and then gaseous iodine atoms initially are 0 because this gaseous iodine atom hasn't produced yet. Okay, because this iodine vapor hasn't vaporized yet, so that's why zero concentration of gaseous iodine atom. Okay, and then what happened? So this iodine vapor starts to decompose. So when this iodine vapor starts to decompose, means this iodine vapor shall decrease its concentration, while this gaseous iodine atom starts to increase its concentration. Okay, good. So therefore, there will be changes in concentration. Okay, for iodine vapor minus X, since it is 1 mole minus X, and for the case of gaseous iodine atoms, okay, plus 2X. And these changes, okay, keeps on going until, okay, both of this iodine vapor and this gaseous iodine atom, both of this reach equilibrium. And at equilibrium, so what happened at equilibrium? The equilibrium concentration of iodine vapor, okay, shall be 0.1125 minus X, while, okay, the concentration of gaseous iodine atom at equilibrium is 2X. Okay, 2X. Okay, class. Remember, in the question, we were given the degree of dissociation of iodine vapor. Okay, alpha, already given in the question. And we know that alpha equals to the changes in the concentration of iodine vapor divided by the initial concentration of iodine vapor. Okay, so in this case, okay, the value is already given, okay, which is 0.0252. And since we already knew the initial concentration of iodine vapor, and this alpha is given in the question, so therefore we can determine what is the changes in concentration of iodine vapor. And once we know this, these changes in iodine vapor, automatically we are going to know what is the value of X. Okay, so let's solve for this. So now let's look at what is the value of X that we are going to get. Right, so by substituting, okay, the initial concentration in this formula for alpha, okay, and then we solve for this, and we are going to get 0.002835 molar class. And this concentration actually also represents the value of X. Okay, so once we have determined this value of X, and then the next step is, okay, right, so we can determine the equilibrium concentrations for both gases, iodine vapor together with gaseous iodine atoms at equilibrium. Okay, so for iodine vapor, its concentration at equilibrium 0.1125 minus X, and since we have already just now determined the value of X, okay, we calculate this, and we are going to get 0.1097 molar. Okay, and then we're going to do the same for gaseous iodine, okay, atoms at equilibrium. The concentration is 2x, remember, from the ice table. So 2x, so 2 times 0.002835. So we are going to get 0.00567 molar. Okay, so now we have already determined both of the concentrations of iodine vapor and gaseous iodine atoms at equilibrium. So once we have determined these two, okay, so finally we can determine Kc class. Okay, so Kc equals to the concentration of gaseous iodine atom at equilibrium squared, because this gas is the products in this reaction, right? Divide by reactant, concentration of reactant. So in this case, the reactant is iodine vapor at equilibrium, the concentration of iodine vapor at equilibrium. So by substituting these two values, okay, this one for iodine here, and you substitute for gaseous iodine atom here, okay, and we are going to get this, right? And then we solve for this. Okay, and we are going to get 2.9306 times 10 to the power of negative 4. Okay. So are we finished yet? No, sorry, we are not finished yet, because we need to determine the Kp value for this reaction. Okay, remember the relationship between Kc and Kp. Remember in question number 10 just now? Okay, but before we're going to use that equation, of course, we need to find out what is the value of delta N. Okay, so now let's look at what is the value of delta N. Okay, so from the equation, right? So delta N. Okay, so now let's look at the product side here. So there are 2 moles of gas here, gaseous iodine atoms, and 2 moles of gases on the product side. And then on the reactant side, okay, there is only 1 mole of iodine vapor. So therefore, to find out what is the value of delta N, so it is 2 minus 1. And we are going to get 1. Okay, and once we have determined this, and then the next step, we are going to substitute all the values that we have known into this equation. Here's equation. Okay, so since we want to determine Kp, So Kc already determined just now, and then R gas constant, T temperature in Kelvin, and then delta N is 1. So by substituting all of these values, class, so let's try to solve for this. So what is the value? What is the value of Kp that we are going to get? What is the value, class? Right. So the answer is 0.0141. Okay, so this is the value of Kp for this reaction. This is the value of Kc, and this is the value of Kp for this equilibrium reaction. Okay, class, so that's all for this lesson. Okay, so I'll be seeing you again in the next lesson. Okay, stay home, stay safe. Assalamualaikum warahmatullahi wabarakatuh. Have a nice day. Bye-bye.